Good day and welcome to this video about the basics of ultrasound imaging. My name is András Nikovic. I'm an intensivist at the Mater in Brisbane. In a nutshell, in medical ultrasound we're transmitting sound waves through various organs and tissues and then receive echoes. These echoes then are processed and displayed on a screen. Sound is mechanical energy that is propagated through a medium by the vibration of molecules. This vibration will make the molecules oscillate about their resting position. Propagation occurs in the longitudinal direction. Zones of high pressure, called compression, and low pressure, called rarefaction, are alternating, creating a sinusoidal waveform. Sound waves propagate or travel through media by interacting with particles, so sound waves cannot travel in vacuum. On the x-axis, there's time, and zones of high and low pressure are alternating. The area between two identical parts of the sinusoidal wave is called one cycle. Important properties of the ultrasound are its wavelength and its amplitude. On the x-axis, there's time or distance, and on the y-axis, there's the amplitude. Wavelength, or lambda, is defined as the distance occupied by one full cycle. Amplitude, or capital A, refers to the maximum variation of particle displacement or acoustic pressure of the sound wave. Other important properties of the sound wave are frequency and the speed of sound. Frequency refers to the number of cycles per second. Unit of frequency is hertz. 1 hertz is 1 cycle per second. Frequency of human hearing is 40 hertz to 15 kilohertz. Medical ultrasound uses frequencies between 2 and 10 megahertz. Speed of sound refers to the rate at which sound waves propagate through a medium. Speed of sound in soft tissue is much lower than in bone. The speed of sound is determined by the density and the compressibility of that medium. Bone is much less compressible than soft tissue, hence the speed of sound in bone is much higher than in soft tissues or in air. The wave equation is describing the relationship between frequency, wavelength, and the speed of sound. C denotes speed of sound, F stands for frequency, and lambda stands for wavelength. The speed of sound is 1540 meters per second in soft tissues, and this is considered constant. Frequency and wavelength have an inverse relationship. As frequency increases, wavelength decreases. The shorter the wavelength, the higher the frequency. This is a very important relationship as image resolution is related to wavelength, while depth of penetration and attenuation of the ultrasound beam are related to the frequency. Attenuation refers to the reduction in strength in ultrasound signals as the wave travels through a medium. Unit for attenuation is decibel. Decibel is used as a standard description of loudness of sound. Decibel always expresses a relative difference between two acoustic signals and is based on a logarithmic scale. I shows the intensity at any point, while I note shows the initial intensity. The table demonstrates the relationship between attenuation in decibel and the percentage intensity remaining or lost. Attenuation, in practical terms, means loss of sound waves and getting a quieter and quieter echo as a returning signal. This limits imaging depth. Degree of attenuation is determined by transducer frequency. The higher the frequency, the shallower the imaging depth. There are a number of factors that must be considered when we describing the attenuation of the ultrasound beam. Absorption means that sound energy is dissipated within a medium. Other forms of attenuation are redirecting the energy of the ultrasound beam, thereby decreasing its intensity. Scattering and reflection form the basis of image formation, and refraction and diffraction will also reduce the intensity by redirecting the energy. Absorption refers to the transformation of the ultrasound energy into heat. This is determined mostly by viscosity and relaxation time of the medium, as well as the frequency of the sound. The higher the viscosity, the greater the resistance to molecular vibration, leading to an increase in friction between molecules, and this converts ultrasound energy into heat. High transducer frequencies will increase molecular motion, also increasing friction, hence absorption is greater too, and this will limit imaging depth. The most important interaction of the ultrasound beam with tissues is reflection, as this is used to create the images. Images are created when sound is reflected at an interface between two tissue boundaries or media. Types of reflectors are specular reflectors, are large smooth surfaces like the diaphragm, whereas rough or irregular surfaces are scatterers. Specular reflectors, shown on the right-hand side of the image, act as a mirror, but this property is angle dependent. Angle of incidence should be perpendicular. When it's close to parallel, dropout of the echoes will occur. Examples of specular reflectors are heart walls with the endocardial border and heart valves. On the left-hand side of the image, there are small irregular surfaces that will reflect the ultrasound beam in multiple directions. These are called scatterers. These reflections are very weak when compared with the specular reflections. Example for scattering is myocardium. A special case of scattering is Rayleigh scatterers. When the dimension of the object is much less than one wavelength, they reflecting the ultrasound equally in all directions. Red blood cells act like this, and this is the basis for Doppler echocardiography. The amount of ultrasound reflected depends on relative changes in acoustic impedance between two tissue boundaries. Acoustic impedance is dependent upon tissue density, shown here ρ, and speed of sound through that medium, c. The table demonstrates different media with different acoustic impedances. Bone is very dense with very high speed of sound. This implies a very high acoustic impedance as well. The amount of ultrasound energy reflected is dependent upon the acoustic mismatch between the two media. The greater the acoustic mismatch, the greater the degree of reflection and the lesser the degree of transmission. At the bone soft tissue interface, 57% is transmitted. At the air soft tissue interface, 99.95% of the ultrasound is reflected. This means that only 0.05% is transmitted. This poor transmission through air soft tissue interfaces is overcome by using coupling gel. The poor transmission through bone and soft tissue interfaces necessitates the use of acoustic windows. Another factor causing attenuation of the ultrasound beam is diffraction. Diffraction refers to the divergence or spreading out of the ultrasound beam as it moves farther away from the sound source. The intensity is less as the same power is spread out over a larger area. With an unfocused transducer, beam starts parallel but then diverges, creating a near zone, that's the Fresnel zone, and the far zone, that's the Fraunhofer zone. Resolution is worse in the far zone. Focusing of the ultrasound beam is achieved by using acoustic lenses, creating a focal zone where resolution is highest. Refraction occurs when the ultrasound beam is deflected from its straight propagation path. This is really the bending of the ultrasound beam. Refraction occurs if these two criteria are met. Firstly, the sound beam encounters an interface between two media with different speeds of sound, and secondly, the angle of incidence is not 90 degrees. Degree of bending is dictated by Snell's law. Dotted line on these images denotes expected path for the ultrasound beam, whereas the bold lines show actual path for the ultrasound beams. On the left-hand side, speed of sound in the red zone is lower than in the yellow zone. On the right-hand side, speed of sound in the red zone is higher than in the yellow zone. In general terms, a transducer is a device that transforms energy by changing different types of energy. The ultrasound transducer changes electrical energy into mechanical energy. Its principal component is a piezoelectric crystal, which is produced from quartz or titanite ceramic. If you apply an alternating electrical current, the crystal expands and contracts repeatedly, generating sound waves. When the ultrasound pulse returns to the transducer and strikes the piezoelectric crystal, an electrical current is generated. The transducer acts both as transmitter and the receiver for the ultrasound waves. Main components of the transducer are the piezoelectric crystal itself, surrounded by damping material, and the outer coating is already acting as a step down for the sound waves, making it easier for them to enter tissues. There are three main types of ultrasound transducers. The linear array is usually used in vascular imaging. Phased array is for cardiac imaging, and somewhere in between there's the curved array, which is mostly used in abdominal scanning. Let's continue with the characteristics of the ultrasound pulses. The transducer emits pulsed ultrasound. After emitting the pulse, the transducer waits for returning echoes and then emits another pulse. These pulses are very short, in the range of 1 to 6 microseconds. The waiting time is much longer. Pulse duration, shown PD on the image, is the time during which the pulse occurs. This is measured in units of time, microseconds. Spatial pulse length, shown SPL on the image, is the physical length of the pulse. This is the distance from start to end of a pulse, and this is measured in units of distance. Pulse repetition period, PRP, is the time from the beginning of a pulse to the beginning of the next pulse. This includes pulse duration plus listening time. Pulse repetition frequency is the number of pulses emitted per second. On this image, pulse repetition frequency is 3 Hz. This is different from the ultrasound frequency. 2D real-time imaging production is obtained by sweeping the ultrasound beam across the imaging plane. Image is formed one line at a time. These lines are then added together to form one frame. Brightness of the dots on the display is proportional to the amplitude of the returning echoes from anatomical interfaces encountered, and the position of the dots is dependent upon the round-trip time of the pulse and the speed of sound in that medium. When we discuss image optimization, we have to consider several factors. Image resolution is the ability of the machine to differentiate two objects and then display them as separate, and can be defined in terms of spatial, contrast, and temporal resolution. Spatial resolution refers to the ability of the ultrasound machine to detect structures that are anatomically separate and to display them as being separate. Axial resolution is the resolution along the axis of the ultrasound beam. Lateral resolution is the resolution perpendicular to the ultrasound beam. Contrast resolution is the ability of the ultrasound machine to differentiate subtle differences in echogenicity between anatomical structures and display these as being different. Temporal resolution is the ability of the machine to accurately show the position of moving structures at a particular instant in time. Axial resolution is the ability of the ultrasound machine to detect echoes from two closely spaced reflectors along the axis of the ultrasound beam. This depends primarily on the physical length of the ultrasound pulses, that is, the spatial pulse length shown SPL on the image. In order for two separate objects to be resolved, they must be separated by a distance which is at least half of the spatial pulse length. Spatial pulse length is calculated from the wavelength and the number of cycles in the pulse. SPL equals lambda times n. Wavelength ultimately depends on frequency. N, which is the number of cycles in a pulse, is determined by the manufacturer and is usually between 2 and 4. After considering these variables, it follows that the shorter the spatial pulse length, the better the resolution. Recall that the shorter the wavelength, the shorter the spatial pulse length. Also, when the higher the frequency, the shorter the wavelength. Ultimately, this is how increasing frequency will improve axial resolution. Let's calculate the resolution of an ultrasound transducer. Wavelength equals speed of sound divided by frequency. Lambda equals C divided by F. Speed of sound in soft tissues is 1540 meters per second. For a 5 megahertz transducer, the equation gives 0.308 millimeters for wavelength. Image resolution is in the range of 1 to 3 wavelengths, so in this case, in the range of 1 millimeter. Lateral resolution refers to the ability of the ultrasound machine to detect echoes from two closely spaced reflectors positioned perpendicular to the ultrasound beam. Reflectors that are both within the width of the ultrasound beam will produce a single echo. To be displayed as separate, they must be separated by a distance that is greater than the beam width. High transducer frequencies come with lower beam width and better lateral resolution. Also, focusing the ultrasound beam will help with lateral resolution. Contrast resolution means differentiating between subtle differences in echogenicity between structures. This can be improved with optimal machine settings and using optimal gain. Harmonic imaging also improves contrast resolution. Temporal resolution is the ability of the ultrasound machine to show the position of moving structures at a particular instant in time. Each image is constructed by a series of scan lines which make up one frame. The higher the frame rate, the better the temporal resolution. Frame rate can be increased by decreasing imaging depth or narrowing imaging width. Both of these mean that there are less scan lines. So how are we going to optimize our images? We should aim to select the highest frequency transducer with the best spatial resolution. However, high frequencies will increase attenuation, and this will reduce depth of penetration. So selecting a transducer frequency is always a compromise between resolution and imaging depth. The use of harmonic imaging gives better contrast resolution. By setting the instrument controls to their optimal value, you can optimize your image quality. Don't forget that depth of imaging affects frame rate, and for deeper structures, more time is required for signals to return. This will reduce frame rate. You should aim for the smallest depth that still allows display of the region of interest. Each machine has a function where you can zoom in or magnify a specific region of interest. Right zoom means magnification occurs during data collection. This improves spatial resolution because there's more pixels per unit area. Read zoom means that magnification occurs after data collection. This doesn't improve spatial resolution any further. Focal zone indicates the region of image where the ultrasound beam is narrowest. Lateral resolution is best in this region. On this image, red dot indicates the position of the focal zone with the best lateral resolution. The returning amplitude of the ultrasound signals is very small, so to produce an adequate image, these signals must be amplified. Gain control does this by affecting brightness of the display. When gain is set optimally, blood-filled chambers are echo-free. With pre-processing, we manipulate data as it is acquired before it's stored in the memory. Time gain compensation, or TGC, adjusts the amplitude or gain of the returning echo signals along the length of the ultrasound beam. Dynamic range is the ratio of the maximum and minimum signal level. Persistence is the smoothing of images. This is done by averaging over several consecutive frames. This causes blurring though, so minimal persistence is used when we're imaging the heart. Edge enhancement makes it easier to detect interfaces or boundaries between structures by sharpening the edges. This gives crisper images. Post-processing, we manipulate data after they're stored. Post-processing curves will introduce more gray shades, therefore they smooth out gray images. B color or brightness color uses a color scale rather than grayscale display. The human eye can only appreciate a limited number of shades of gray, but it's able to distinguish a greater number of different hues of other colors. Reject sets the minimum echo level that will be displayed, this way removing electronic and acoustic noise. To date, there have been no known adverse biological effects of diagnostic ultrasound. However, the potential for bioeffects does exist. Bioeffects refers to the potentially adverse effects in tissue, and it's categorized as thermal effects and mechanical effects. Thermal effect is the heating of tissues by attenuation or absorption of the ultrasound beam. This converts ultrasound energy into heat. Thermal effect depends on output power, transducer frequency, and exposure time. The thermal index, Ti, is displayed on the ultrasound screen. Mechanical effects comprise of cavitation and microstreaming. Cavitation occurs when sound waves interact with microscopic gas-filled bodies. In theory, this may lead to rupture of cell membranes and high-velocity fluid movement ensues. Other times, localized shock waves may be produced by growth and violent collapse of these gas-filled bodies. Mechanical effects depend on transducer frequency and exposure time, and it's displayed on the ultrasound screen as well, MI. Because there is a potential for bioeffects to occur, the ultrasound equipment must be operated as safely as possible by applying the ALARA principle. ALARA stands for as low as reasonably achievable. This means that ultrasound examinations must only be performed when clinically indicated and only for the shortest possible time with the most optimized images. Thank you for your attendance.